All right, today we're looking at the integral and p-series test. Integral test is if f is positive and decreasing for x greater than or equal to 1 and a sub n is equal to f of n, then the series or the sum from n equals 1 to infinity of a sub n and the integral from 1 to infinity of f of x dx either both converge or both diverge. There's a lot of fancy words for saying, hey, if you turn your sequence into a function and you integrate it from 1 to infinity, then if that integral converges, so does the series. If that integral diverges, so does the series. Now, the big thing here is it doesn't tell us what it diverges or converges to. So that's what we have to keep an eye out for. So let's start with one that converges. So we look at number 2 here. Ignore number 1, we'll come back to number 1. Look at number 2. We're thinking to ourselves, okay, what test to use? We start with nth-term test, and we do it in our head, because we don't need to write the ones that don't work. Nth-term test, we go to infinity, we see it equals 0. Nth-term test is not going to work for it. It's not geometric, it's not telescoping, because we can't break it apart into two fractions that are subtracted, so we're going to try our integral test. The first thing we do is we write what f of x is. F of x in this case is 1 over x squared plus 1. And then we set it up as an integral from 1 to infinity. Now, we've done improper integrals, so we're going to go ahead and change that that infinity to b. 1 over x squared plus 1 dx. And we'd say that the limit as b approaches infinity, integral of 1 over x squared plus 1 is arctangent of x from 1 to infinity, or 1 to b. Plug in the upper and lower bounds. What is arctangent of 1? Well, that's pi over 4. We know that. And then as b goes to infinity, we saw this in the improper integrals unit. Arctangent is going to go to pi over 2. So that's going to be pi over 2 minus pi over 4, which equals pi over 4. All right. Nothing too crazy there. So our integral went to pi over 4. Now let's create a statement for this. We say therefore, oops, this one's a little weird because I'm going to say therefore and then since the integral from 1 to infinity of f of x dx equals pi over 4, or you can say converges to pi over 4, either one will work, then the series also converges by the integral test. Okay, the series also converges by the integral test. That's it, just doing the integral. Now this is more of our brute force method. This is the one that as long as you can integrate it, it would work. There are a few cases where you won't be able to integrate. The issue is it's not always the most efficient method. We're going to have plenty of cases where it's not as efficient as something else. This one up here, if you want to work it yourself, it should diverge. So make sure when you're integrating, you should be able to use substitution when you integrate. It should get something that diverges. All right, like for example, this one. We could do the integral test. We learned last semester how to integrate something to the power of x. We could, but it's not the most efficient way. This is a geometric series. The r is equal to 1/2, which is less than 1. So we can say the series converges to, and we can figure out what it converges to. I think this one converges to 1. By the geometric series. Now, in most cases, it won't matter what test you use. It's not going to matter at all what test you use. They're all going to give you converges or diverges, unless you can use geometric or telescoping. If you can use geometric or telescoping, then you need to use it because it gives you what it converges to. So my answer here is more accurate than if someone tried to use the integral test. All right, so making sure we keep that in mind is also very important. All right, these are just some we can do in our head, and they're just to prove a point, so we'll get to the point they're trying to prove, and that is the p-series. We say a series from 1 to infinity of 1 over into the p is called a p-series, And a p-series converges if p is greater than 1, diverges if p is less than or equal to 1. So let's look at some examples. Right here, we have 1 over into the 5th. Well, our p in this case would be 5, which is greater than 1. The series converges by p-series test. That's it. That's all it is. All right, we do the same thing for 5. 5, p is equal to 1/2, because that's what that fraction is, which is less than 1. So the series diverges by p-series test. Now, the big thing in ones like number 6, if it's a constant multiplied in, we can pull that out and still use p-series. If this was 3n plus 1 or 3n minus 1 or something, then we would not be able to use p-series because it has to be constant over into a power. All right, that's what it has to be. So we'll pull out the 4/3 because it's just a sum, and that 4/3 can come out and won't affect the final sum. In this case, p is equal to 1, which is equal to 1, and that tells us that the series diverges. By p-series test. All right, so that's the integral test and the p-series test. Integral is very straightforward. Integral from 1 to infinity. If it converges, series converges. If it diverges, the series diverges. P-series, it's just if p is bigger than 1, it's going to converge. P is smaller than 1, it's going to diverge. Smaller than or equal to 1, it's going to diverge. Once again, neither of these series tell you what it converges to. So you will not be able to say what it converges to in these cases. All right, let me know if you have any questions. You'll have a great day.